All right, guys, welcome to Unit 5, Derivatives, Part 4, review notes. So let's begin here. All right, let's talk about extrema first. There are two types of extrema. One type is the relative or local extrema. What are those? Well, there's a relative max and there's a relative min. A relative max is a point where a y value is greater than any y value to its immediate right or left. So it could look like this. That would be a relative max right there. Or it could look like this. That would be a relative max at the very top of the curve. Or it could look like a jump of some kind, which maybe, let me see if I can sketch one here. So in that case, this point up here is higher than any point to its immediate left or right. Okay. And likewise, when it comes to the relative minima, we have the same thing. It's just inverted. So relative min could look like that, or it could look like maybe that. Okay. So those are what relative extrema are. Relative extrema occur at critical values. That's the places where the derivative is 0 or undefined. So like, for instance, on these curves here, that's where the derivative is 0. You have a flat horizontal tangent line. But for these cusps here, or for these jump discontinuities, those are places where the derivative is undefined. And so relative extrema always occur at critical values. And critical values are those places where f prime is either 0 or undefined. The other type of extrema are the global, also known as the absolute extrema. And those are the highest and the lowest points on a graph. So, maybe I could draw a graph like this, for instance. So the difference about the absolute extrema is that an absolute extrema can be a relative extrema. Like this is a relative minimum, but it's also the absolute min because it's the lowest point on the graph. But unlike the relative extrema, absolute extrema can occur at the endpoints. So the absolute max is here, whereas relative extrema don't occur at endpoints because they have to be at a point where the y value is greater than any y value to its right and left. But if you're at an endpoint, you don't have a right and a left. It only has one side to it. So absolute extrema or global extrema can occur at endpoints or at relative extrema endpoints. All right, so that is extrema. Now, there's a theorem we call the extreme value theorem, abbreviated EVT, and it states the following, that if a function is continuous, meaning there's no holes, gaps, or jumps, and it's on a closed interval, that means that the endpoints are defined. So it doesn't matter how I draw this line here, so long as I have a continuous line and the endpoints exist, then there has to be an absolute max or min somewhere on the interval. Notice that this theorem does not tell you what they are. It doesn't tell you what the absolute min and max are. It just tells you that they do, in fact, have to exist. And the benefit of that is that if you know that if they have to exist, then that means that they're worth looking for. All right. So here's an example here of an EVT type question that I thought I would include for you guys. Which of the following functions of x is guaranteed by the extreme value theorem to have an absolute max on the interval 0, 4? Well, notice we have a closed interval, so that's good. So the only thing we really need to check to make sure is, are these functions continuous on the interval 0 to 4? And it turns out there's only one that is. The only one that's continuous on 0, 4 is this one here in the middle. Now, I gave you guys a sheet a little while back that shows you where various functions are discontinuous. It's, go ahead and take a look at it. I think it was in lesson 3.2 or 3.3, but it's the continuity of common functions. You might want to look at that. That'll help you understand these kinds of things. But tangent has vertical asymptotes everywhere, like all over the place. Rational expressions, the bottom can't equal 0. Same thing. This is a rational expression also technically, so that can't equal 0. So all these things have places where the bottom equals 0. Now, it's okay for the bottom to equal 0. It's just that those 0 places cannot be on this interval. And it turns out that every one of these, if you were to go through and check them, would have a place where x is somewhere between 0 and 4, and it makes the bottom equal 0. So these ones all fail, and the only one that doesn't have any discontinuities is that guy right there. So the answer is B. Okay. All right, so intervals of increase and decrease. So how can you tell where a function is increasing and decreasing? Well, if f prime, if the derivative is greater than 0, that means that f of x is increasing. And if f prime of x is less than 0, that means the function is decreasing. So that leads us to the first derivative test. The first derivative test is a test that we use to find the relative extrema of a function. And here's how it works. If you can find a point that's defined, and the derivative changes from positive to negative at that point, then it's a relative max. Let me give you an example. So say this point here exists, and the derivative changes from positive to negative. In other words, the function goes from increasing to decreasing at that point. Well, therefore, we must have a relative max. It's important to notice, by the way, that it's relative extrema. It's not absolute extrema. There's another test that we'll talk about in a moment that tells you the absolute extrema. But the relative extrema can be found with the first derivative test. So if you can show that the point exists and that the slope changes from positive to negative at that point, then that point must be a relative maximum. Likewise, if the point exists, but the derivative this time changes from negative to positive, so the point exists, but the slope goes from negative to positive, then you must have a relative minimum at that point. Okay, and that's the first derivative test. Now here's an example of how to do it, right? This, you guys can ignore that. That shouldn't be there yet, but just ignore it. So step one is to find the derivative of your function that they give you. So here's the function, and here's its derivative. The next thing you're going to do is you're going to set it equal to 0 and solve. So I get 0 and 2. Okay, that's how you find the critical values. Now another thing that you're supposed to do to find critical values, you're supposed to find where it's undefined. But I didn't do that here because polynomials are never undefined, so there is nowhere that it's going to be undefined. But when you find your critical values, you do look for the places where it's both undefined and equal to 0. And by doing that, I get 0 and 2. So those are my critical values, and that's where the relative extrema could possibly occur. So now I'm going to identify my testing intervals. I'm going to make a number line. I'm going to put these two numbers on that number line, boom and boom. And that means we have 3 intervals to test. From negative infinity to 0, 0 to 2, and 2 to infinity. And what we do to test those is we pick some points in those intervals. So from negative infinity to 0, I'll pick negative 1, and from 0 to 2, I'll pick 1, and from 2 to infinity, I'll pick 3. And what I'll do is I'll plug those into my derivative. Now, by doing that, I end up with a positive answer here, which means the slope must be increasing. And for this one, I get a negative number, which means my slope must be decreasing. And then for this one, I get a positive, which means my slope must be increasing. And so from here, you can kind of tell from the shape of the graph that this point right here, which was at 0, must be a maximum. And this point right here must be a minimum. So f of 2 is a minimum. And that's what we call the first derivative test. So find the derivative, find the critical values, do a number line test, draw a picture, and you've got your answer. Okay? So that's the first derivative test. Now, the candidates test is another way to find extrema, but this one helps you find the absolute extrema. Okay, the candidates the candidates, meaning the possibilities, the possible things that can be the absolute min or max. The candidates will occur at one of two places. They will either occur at the critical values, that's the place where f prime is 0 or undefined, or they'll occur at the endpoints, because remember, when you're doing absolute extrema, endpoints can be included. Okay, so that's the candidates test. And that's the one that we usually make the little table for, in case you forgot. It looks like this. You put your candidates over here, you find the y values that go with it, and you just find the biggest and the smallest ones, right? So that's the candidates test. So let's go ahead and take a look at an example of that. So this example here says, find the absolute extrema of this function on this interval. So step 1 is to find the critical values, because that's one of the places where the absolute extrema can occur. So we're going to find where f prime equals 0. So I find the derivative of this and set it equal to 0. And I also find where the derivative is undefined, but that doesn't apply once again because this is a polynomial. So I only have one critical value, and it's at 3. All right. Step 2, make a table that includes the endpoints and the critical values from step 1. So here's my table. I'm going to include the 1, the 4, and the 3 under my x column. Step 3, we just plug those numbers into the original function, because that's the one I'm trying to find the max or min of. And after we do that, we can identify our max and our min. So the maximum value must be 5, and the minimum value must be 1. And so that's the candidates test. So we have 2 tests so far. We have the first derivative test, which helps you find the relative extrema, and we have the candidates test, which helps you find the absolute extrema. There's actually one more test, which we'll get to in a little bit, and it's just another way to find relative extrema in a different way. So we'll look at that one in a second. First of all, let's talk about the second derivative and concavity. Anytime the second derivative is greater than 0, that means your function is concave up. Anytime your second derivative is less than 0, in other words, it's negative, that would mean your function is concave down. So that leads us into that last test I was telling you about, the second derivative test. This is a test, once again, to find the relative extrema of a function. Now, sometimes this test is easier, so people like to use it, but sometimes it's inconclusive, okay? And you'll see in the example how this can occur when we get there, but for now, it's inconclusive anytime the second derivative is 0, okay? So if you end up with the second derivative equaling 0 at the point you're testing, then it's inconclusive, and when that happens, you have to go, darn it, I wasted my time, go back and do the first derivative test instead. Okay, so it is easier, especially for polynomials, but it can also waste your time if you're not careful. But there's also just some questions where they deliberately word it in such a way where you have to use the second derivative test instead of the first, so be aware of that. So here's an example of the second derivative test. I'm going to be using the same example we had before, so I want to find the relative extrema of this function. So step 1 is to find the first derivative. Find the critical values by setting it equal to 0 and solving, and I get 0 and 2. Once again, you're also supposed to find where it's undefined, but once again, that's pointless because that's a polynomial and they're never undefined. Okay. Step 3, now we want to find the second derivative. This is where it gets a little bit different than the first derivative test. So I'm going to take my first derivative here, and I'm going to take the derivative of that, and that gives me 6x minus 6. Now here's where things get interesting. I'm going to plug my critical values into my second derivative and see what I get. So if I plug my first critical value 0 into my second derivative, I get negative 6. Now what is that? And if I plug 2 in to my second derivative, I get 12. So what does this tell me? Well, negative 6 is less than 0, which means that my graph is concave down. Now, if your graph is concave down, that would mean that point in the middle, f of 0, must be a maximum value. Likewise, since this one over here, the 12, is greater than 0, that would mean my graph is concave up, which means that f of 2 is a relative minimum. So this is an error. I need to fix that. That should say minimum. Okay? And I actually should, you can actually even add this too, because they're relative minima and relative maxima. So you might want to put the words rel on there also. Okay? But that's the second derivative test. So find the derivative, find your critical values, find your second derivative, plug those critical values in, and come to your conclusion. All right? Let's go ahead and move along here. Another thing that we're going to be doing in this particular unit is comparing the graphs of f and f prime. So this is just something to think about. You're going to use this table if you're given a graph of f, and then you're asked to make some conclusions about f prime. Now just so you know, this is not a very common way the question is asked. Usually they give you the graph of f prime and ask about f, but I just wanted to give you this just in case. So this is kind of like maybe not so important of a slide. But I'll let you guys just have that as a reference. But that being said, let's go ahead and go on to the next slide, and I'll spend a little more time on this one because this is the more common thing. Anytime you're given the graph of f prime and asked something about the original function, here's how you can draw some conclusions. Anytime the graph that they give you is above the x-axis, that means f is increasing. So if the graph that they give you, which is a derivative, is above the x-axis, that means f is increasing. And why is that? Because if f prime is above the x-axis, that means that f prime is greater than 0, and as we already mentioned in this video, that means that the function's increasing. Contrary-wise, if f prime is below the x-axis, that means that f prime is negative, and therefore f is decreasing. Now, whenever f prime actually crosses the x-axis, there's two ways that could happen. Let's say this is the x-axis, and let's say that my graph going from left to right crosses this way. Okay, well, it goes from being below the x-axis, I'll put B for below, to above. Okay, well, since the f prime graph is going from below to above, that means that f prime is going from negative to positive. And we talked about that earlier in the video also. Anytime you have a point and the graph goes from negative to positive, that means the original function must have a relative minimum at that point. And so if the f prime graph goes from below to above the x-axis, that is a point where the f function has a relative min. And contrary-wise, anytime the f prime graph goes from above the x-axis to below, so I'll draw that as well. So if the graph goes like this, goes from above to below the x-axis from left to right, that's a place where you have a relative maximum. Now, if f prime is increasing, that means that f prime is going in an upward direction. That means that the original, now this takes a little bit more thinking, so let's be careful. So if f prime is increasing, what that means is that the slope of f prime is positive. The slope of f prime is the second derivative. So if f prime is increasing, its slope, in other words, f double prime, is greater than 0. And we talked in the video earlier about how that means that f is concave up. And contrarily, if f prime is decreasing, that means that f double prime is less than 0, and therefore f is concave down. And anytime f prime anytime f prime has a relative min or a max, like here or here, for instance, that means its slope is going from positive to negative, or it could be negative to positive. It doesn't really matter. Anytime its slope is changing, that means that f prime changes signs. The slope of f prime, in other words, f double prime, changes signs. And anytime f double prime changes signs, it's going from concave up to concave down or vice versa. And that is a point that we call the point of inflection. So this is the more common way that these questions are asked, where they give you a graph of f prime and ask you to draw some conclusions about f double prime. And these are the most common types of scenarios that they will ask about. So keep that in mind. And just so you guys know, I didn't memorize this stuff. It's just stuff that you figure out, right? So for instance, f prime is above the x-axis. Well, that means that f prime is positive. And if prime is positive, that's f prime is the slope of f, so that means that the slope of f is positive, which means it's going up, which means that f is increasing. So it all just makes sense. You don't necessarily have to memorize it if it makes sense. But if you want to throw these on some flashcards to help yourself out, you're more than welcome to do that. All right, now we're going to get into a special type of word problem called optimization problems. What are these? These are a word problem where you are asked to find the greatest or the least value of some measurement. And basically what these are is these are just candidates test questions. They're not going to look like a candidates test, but they really are. That's what you're trying to do, is you're trying to find the absolute max or min. So let's go ahead and take a look at an example here. Now, so these questions are like, to me, these are a little bit like related rates, in that they're a little bit hard. And there's so many different ways we could ask the question. But here's the thing. Optimization problems are not that important, honestly. They're just not a big deal. There's just not too many of them on the AP exam, in my opinion. Yeah, we'll go over it just in case. But related rates, which we talked about last week, those are super important. Make sure you know related rates really well. But let's take a look at this one. So the question here says find all the points x, y, so that would be like this, for instance. Find all the points along the curve where the rectangle, this thing here, inscribed inside the semicircle will have the greatest area. So I mean, for instance, if you were to put the points here and here, you're going to have a really flat rectangle, and chances are the area is not going to be very good. Or if you put them too far up here, then your rectangles are going to be really long in a vertical direction. You're still not going to have much area. So we need to find a place where should I put the dot along this curve so that this rectangle ends up being the greatest possible area. All right, so oh, that was not supposed to come up yet, so you can ignore that. We'll get to that in a minute. The step one is to write a function for the value you want to optimize. So I want to optimize the area of the rectangle. I want to find the greatest area. So how do you find the area of a rectangle? Well, the area of a rectangle is base times height, right? Now, the base is x plus x, which is 2x, and the height is the y value, which they've given us here. So my base is 2x, and my height is the square root of 4 minus x. So the area of the rectangle is 2x, that's the base, times the height, square root of 4 minus x squared. Now, this is the thing that I want to find the minimum or maximum of. Okay, so whenever you want to find a minimum or maximum, you need to find the critical values, and you do that by finding the derivative. So let's find the critical value. Step one is to find the derivative. That's this right here. I did that. It would take some time to get to this answer. You would have to do a product rule, and after you do the product rule, you'd have to make common denominators. But I'm going to skip all that work for now. I'm just going to say, okay, find the derivative. There it is. Step two, find where it's 0 and undefined. Now, this is a very important note for today, even though I'm telling you optimization is not important, but this question is important. Anytime you want to find critical values of a rational expression, you set the top equal to 0, and you also set the bottom equal to 0. When you set the top equal to 0, that's when the function equals 0. So when I do that, I get plus and minus square root of 2. If you want to find where the function's undefined, this is supposed to say a prime, by the way, not a. But if you want to find where a prime is undefined, then you set the bottom equal to 0, and for that I get plus and minus 2. Okay, so I have 4 critical values, and I'm going to put them in my table. Now, usually when you do the candidates test, there are some endpoints, and there's a way to do endpoints on here, but usually they don't even include it. So I'm just going to go ahead and leave it out. The endpoints would be -4 and +4. But I mean, obviously, that's not going to work because if your rectangle was here, it would be flat and completely 0. So we don't even care about that. But you could include the endpoints -4 and +4 if you wanted to. Anyway, so there's that. So let's review what we have so far. So step one, find a formula for the value that you're trying to find the greatest or least value of. Step two, find your critical values by finding the derivative and finding where that derivative equals 0 and also where it's undefined. Okay, so let's continue on. Then you do your candidates test, which basically means you're just going to take these x values and plug it into your original function and see which one gives you the greatest area. -2 gives me an area of 0, apparently. Negative radical 2 gives me an area of -4, and these just don't even really make sense, honestly. You can't have an area that's 0 or -4. Radical 2 gives me 4, and 2 gives me 0. And so we could see that right here, the point x, y that will give me the greatest possible area is radical 2. That's the x value. And to find the y value, you just need to plug that into this expression here, because that's your formula for y there. 4 minus radical 2 squared. Radical 2 squared is 2, and 4 minus 2 is 2, and you just end up basically with radical 2. All right, so there's our final answer for that one. And that's it. So that's some of the topics we'll be looking at for the first half of the week. So keep these notes handy and bring them to class with you so that you can reference them as you're going through the problems. And we'll see you guys in class. Bye-bye.